75 factorial, huge number, probably close to, what, 600 digits, maybe something like that. 275 factorial upon division by 277 leaves a remainder 1. Now, a lot of people would prefer to see this form. That's the very same thing as using, our conventional equality symbol and writing it as a multiple of 277 plus 1. Okay, and m's just going to be a positive integer, of course. Okay, now, so this, the way I just wrote it is nicer looking, but notice that m is almost unfindable. In other words, that would be what would happen if you divided 277 into 275 factorial, which is, again, I think approximately about a 600-digit number. So we have to resort to, or I'm going to resort to modular arithmetic. Now, take a look right here. 275 and 277 are kind of close, and a lot of you probably already recognize the path here. The way I've written this is a special case of the well-known result by Wilson, p minus 1 factorial. Okay, p minus 1 factorial congruent to negative 1 mod p. That's a standard result in a number theory book, and everything is relatively prime, and you can just kind of pair up the factors because they're congruent to 1. But let me put mod p here. Okay. Now notice I wrote down, this is just to get us to terra firma. Now proving 277 is prime is not too hard. All you have to do is check everything less than 17. The square root of 289 is 17, and 277 is less than, so all you got to do is check the prime factors less than 17 to verify that 277 is prime. Now, so I rewrite Wilson's theorem in this fashion. Why did I do that? Because if you write 276 factorial like this, you get the 275 we're looking for, right? Okay. Now, so here we go. So we're just re-expressing it in a fashion where we can get 275 exposed right here. Okay. Now, notice that this particular truth right here is going to come in quite handy. 276 squared times 275 factorial is congruent to minus 276. How did I get that? I multiplied through by 276. Okay, I multiplied through by 276. Now you may go, well, what motivates that? Well, notice that minus 276, right, is congruent to 1. Okay, so that's good news, right? Minus 27, let me just write this down right here. Minus 276 is congruent to 1. So that kind of motivated multiplying through by 276. Now it turns out there's another nice thing going on with 276. Let's go down to the next line. 276 squared is 277 minus 1 times 277 minus 1. That gives us this expression. But notice right here, if you factor out a 277, you get 277 times 275. Plus 1. Now, so you see, we get this remainder of 1 right here. And so this implies that 276 squared has to have a remainder of 1 upon division by 277. This fairly simple arithmetic right here leads to this truth right here. Okay, now that's a big deal. That's a very big deal because 276 squared congruent to 1. Okay, we can just replace 276 squared with 1, and we get this statement right here. Now we've already indicated that minus 276 is congruent to 1, and so really we're done with what we tried to prove. In other words, this tells us that 275 factorial is congruent to 1. And of course, we are talking about mod 277. So that completes the proof. Now, let's see, folks. You may have noticed I did a video not too long ago on where I proved this result right here. The general result really is something that looks a lot like Wilson's theorem, but it's a little different. You have a prime p minus 2 factorial in general. P minus 2 factorial is congruent not to -1 but to 1. Now I just went through all the arithmetic. I could have started out stating this as a factor, proving this, and just writing down the answer, but this is congruent to 1 mod p. Again, some resemblance to Wilson's theorem, but slightly different in appearance. Okay. All right, y'all, I guess that's it. Let's see. Is that what we tried to prove? We're trying to show that 275 factorial is congruent to 1. That's what we did right down here. So we can put a box here, I suppose. Okay. Okay, y'all.